Hello, in this section I'm going to talk about mean value theorem. So mean value theorem is actually pretty nice because essentially you have that, let's say that, we're looking at our x and y axes. So if we have that we look at the x and y axis and let's say that we have a function. Now it kind of doesn't matter what kind of function we have, but let's say that we have a function like so. But let's say that I go ahead and I pick a point right here. So like let's say this right here is A, and then let's say that I pick another point like this one, like B. So over here, notice that, okay, we can form a line that passes through both of them. But then note that, for example, that we can form another line of which runs approximately parallel to here. It's going to be a little difficult, but let's just go ahead and try. Okay. So we'll call that point that gave us that tangent is C. So what mean value theorem says is that there exists a point C such that the slope of the tangent is actually equal to the slope of the secant. Okay, now this is actually pretty useful for a lot of applications, mostly in proving that minimums and maximums exist, but also in showing like what some approximations of endpoints might be. So let's go and look at this. Let's say that we take an example, and let's say that we have f of x is equal to x squared. So we'll do x squared plus 1, and we're going to look at it from the open interval from 1 to 3. Okay, well, we can calculate f of 3, which is 3 squared plus 1, which is just 10. We can also calculate f of 1, which is really just 1 plus 1, which is just 2. Now, of course, if we go ahead and we find the derivative of the equation is equal to 2x. Okay, well that wasn't too bad. So we have that if we go ahead and we set the derivative, so we have 2c equals to 10 minus 2 divided by 3 minus 1, which is 2c equals to 8 divided by 2, which is really just 4. So we have that 2c equals to 4, so c is equal to 2. So we have that when the slope of the tangent is equal to the slope of the secant is at 2. Now, one thing that's kind of interesting is that mean value theorem actually implies that you have to have a closed interval from a to b and that the function has to be differentiable, which means that it's continuous, but it doesn't have to be just one point. It can actually be more than one. So like for example, but it has to be contained within the interval. So let's say, for example, that you have f of x equals to x cubed minus 2x plus 1. And let's say that you were looking at it from 0, 0 to 2. Okay, well, we know that f of 0 is just 1, and that f of 2 is going to be 8 minus 4 plus 1, so that's going to be 5. So we need to basically plug this into our equation. So we have f of x prime is 3x squared minus 2. Okay, well that means that you have 3c squared minus 2 equals to 5 minus 1 divided by 2 minus 0. But this is really just 2. So that means that 3c squared equals to 4. So we divide by 3, and we happen to get that this is going to give us c squared is equal to 4/3. But if I take the square root on both sides, note that c is equal to plus or minus 2 over root 3, which is the same thing as plus or minus 2/3 root 3. However, there's a problem. Negative 2/3 root 3, it actually is not contained in the interval from 0 to 2. So what that means is that the only value of which gives us the satisfying mean value theorem is 2/3 root 3. Now, interestingly enough, you can actually find, for example, one of which that you can apply this to, let's say, like the mean value theorem. I'm sorry, you can apply the mean value theorem to, let's say, like the absolute value function. So, for instance, um, let's say that you want to try the equation g of x equals to the absolute value of x minus 1, and then this will be on the bounded interval from 0 to 2, and see what happens. Okay, so try to use mean value theorem for this, and then if you get a chance, go ahead and try again. Let's say for the square root of x from 4 to 9, and then see like what values would satisfy mean value theorem for that one. Okay.